Okay, hey everyone. Let's take a look at the big picture of observer designs, which is the topic that we started last time. Observer design is the concept of, that having the state of a dynamic system is going to give you amazing power in terms of control design. But the reality is you only get the measurements, which is not directly the state, but is a linear combination of the states. Now, to get this estimate of the state, what we do is we have a copy of the model of the plant, not the exact copy, but some slight changes in the copy, in the way that we have the A, B matrices embedded in the state equation of the observer, and then we add the difference. We sort of add a correction term between the actual output and the observer estimated output. If the observer is designed very well, then these two should match together. But in reality there are differences usually, and we use this arrow to drive this copy of the plant. So we use this arrow to drive the observer state estimation like this. It's a simple static gain multiplied with the arrow between these actual output and estimated output. And if we plug in the model of the output y and the estimated output y hat, so estimated output is a copy, it's the same model as the output, but with the state replaced with the observer estimate. Plug these two inside here, you will arrive at this equation that depends on the right-hand side. The observer depends on the estimated observer state x hat as well as the actual state x. So the information from x is actually fed back into the observer. There is this internal feedback loop, and then feedback creates the correction over here. This is the observer dynamics. We derived last time how the error between these two, x and x hat, they evolve. And then the error from last time is E dot equals A minus LC E. Basically, you extract this equation from this equation, and then you would get this equation. The way that we usually treat these two things together is to augment these two set of dynamics. So there are two set of differential equations, x, one about x, another about x hat. So overall, this entire thing considered together, this is actually a augmented dynamic system. If the dimension of the plant is n, you have a copy of the plant here. So you have another nth order differential equation in here. Augment these together, this is entirely a new dynamic system. So we would write augmented system. We would combine these two. For this, treat this as the entire augmented model. Then you would have one is about x, another is about x hat. For this new system, it has two sets of states. One is x hat, and then the differential equation that describes them from the state to the derivative of the state is, so just combine these two together, we would have x dot equals A times x. It doesn't depend on x hat, so it's 0 times x hat plus b times u plus b times u here. And then for x hat dot, it depends on x. It depends on LC times x, so it's LCx. And then it depends on x hat in the way of A minus LC times x hat. And then it depends on b times u. So that is the overall augmented system. the dynamics here, we can write it as x and x hat as the augmented vector. For analysis purposes, we can also write it as replace x hat with the difference between x and x hat. So you can see that this is also a way to select the state variables for this entire system, because you can see here, this is nothing but a linear transformation. This set is a linear transformation from this state variable choices. And if you select it this way, the benefit is you can still write it. The first part doesn't change. Dx is still a times x plus b times u. And then the aerodynamics is a minus LCE. It doesn't depend on x directly. So it's 0 a minus LCE. And it doesn't depend on u. So it's 0 times u. This alternative representation of the state system is diagonal in the overall augmented A matrix, and is convenient for analysis. Here, this is a intuitive representation of the entire system. It explains the concept, but it doesn't tell us too much details about how this exact updates looks like. Or in other words, you have to look at the equations to really understand what's going on in this observer design. We can make this a little bit more explicit. We can add a little bit more information into this block diagram and make it more complete. So the way we're going to do is we're going to write this set of equations into the block diagram. For this plant, we know how to write this state equation in a block diagram. So we have the control input U first goes through the B matrix, becomes BU, and then we have x dot equals BU plus AX. So we have an integrator over here. This is X, and then AX plus BU generates X dot, and X dot integrated becomes X. So that's how to write the state equation in a block diagram. And then the output is C times X, gives you the output Y. The observer can also be written in a similar workflow. So we have U going through also B. So we have BU now. And then BU plus AX hat. So it's a similar copy concept. This is X hat dot BU here. X hat. So BU plus A times X hat. And then plus L times Y minus Y hat. So we get Y and Y hat like this. Here I assume, so for this is Y equal to CX. I'll just work on the Y equals to CX. There's no DU term for simplicity. If you have a DU term, the story is similar. So you just draw another line from U to Y and then add them up. Add that line up with this one. All right. The observer is going to use L times the difference between y and y hat. We have the difference now. And then the observer adds, on top of the previous summing junction, it adds L times this difference. So that is more precisely what we mean by having a copy of the plant and then updating this plant copy with the arrow between y and y hat. In MATLAB Simulink, for example, you can construct the entire observers using all these blocks over here. Or you can construct using M script, or in Python using this set of equations. Over here, I have done an observer design for you in the book. It's in example 12.21. This is a motor control example. So to run this in Python, you import the usual toolboxes, NumPy, the plot function, and I use a bunch of tools in control MATLAB. So I define ABC matrices in these NumPy arrays. To do the observer design, I first check whether the system is observable or not. If it's observable, then we can design observers to place arbitrarily the eigenvalues of the observer dynamics. So here I just computed the rank of the observability matrix. You can see it's C times A, C times A square. So that's observability matrix. And then I check after checking this, it's indeed observable. And then the way I design the observer gain L is to place the eigenvalue of the A minus LC matrix here. So I'll place the eigenvalue of this matrix at negative 500 plus 250J. Complex eigenvalues comes in a set. And then I define the other eigenvalue at negative 1000. And then the observer design of L can simply be obtained by using this place function. So I say I place the eigenvalue of the observer at the poles of the desired observer locations. And then I input A matrix and C matrix. So these are the two variables over here, the arguments over here, the A matrix and the C matrix. So I have run the simulations exactly constructing the block diagram like this, the system equations on this side, and then this is the result. So the motor has 3 states. One is the current, and then the other is the angular position and angular velocity. So you can see I plot in the solid line, this is the actual state values, and then the dashed lines are the estimated from the observer. You can see the convergence is pretty quick. After 0.01 second, then the convergence is achieved. The dashed and solid lines match with each other. You can download the full set of code from this link over here. The observer in this format, continuous time observer in this format, is called a Luenberger observer.